title, why did humanity take one? 000 years to understand wind. 10-day. Thumbnail design evolution. A documentary-style science history story in 1,888 inches, Cleveland, Ohio. Charles Brush built a strange wind machine, 144 cedar blades. Like a ceiling fan for Greek gods. By modern eyes, it looks
Mr.
awkward.
Davies.
Hundreds of small
The
blades.
future of illumination.
Steep pitch. Sluggish motion, yet it quietly powered Brush's lab. Brush
That should
followed
hold
a
the
1.
torque.
000
Now, let's see if she
year
turns.
belief. Wind was a
Careful up
crude
there,
force.
men.
And to control it, you simply needed as much surface area as possible. Yet a century later, we face a paradox. Brush used 144 blades, but we use just 3 and generate hundreds of times more power. What changed was not only science, but mindset, from treating wind as resistance to conquer, to treating it as energy to optimize. To see this intellectual turn, go back to an era when wind power wasn't measured in kilowatts, but in sacks of grain per hour. Through the Middle Ages into the 19th century, windmills weren't aerodynamic elegance. They were heavy-duty machines built for torque. They pumped water from Dutch fields, ground grain, and milled stone, tasks needing high torque, not high rotational speed. To get that torque, builders enlarged the wind-catching area, creating many bladed designs with sail-like surfaces driven by drag, like holding a board into the wind. Drag hits hard but moves slowly, effective for labor, yet inherently limited for fast rotation. Mechanically, many blades also gave natural stability, mass spread out, forces continuous, and fewer aerodynamic shocks to the structure. That is why Brush's 144 blade rotor ran safely for decades, turning steadily even when the wind off Lake Erie was uneven and low. But stability carried a price. Drag-dominated rotors hit a speed ceiling, since every revolution wastes more energy fighting the air. This matched the pre-electric world,
The wind generates
but it
lift
failed in
and
the
drag
age of
on the
electrification.
blades, creating a
When history
rotational
drew a new
force.
line, we needed
This
fast
force,
RPM.
visual-
Once electricity became the goal, engineers met a ruthless truth. Generators demand high rotational speed, not just raw pushing force. Design thinking shifted from capture as much wind as possible to keep the airflow as clean as possible, minimizing losses. Energy conversion explains it. The rotor must spin far faster than traditional mills ever did. So designers began a structural purge. Blades were made slimmer, the blade count was reduced, and pitch was optimized to cut drag while increasing lift like an aircraft wing.
The
Then came
voltage is
rotational
climbing
inertia.
steadily with the
Each
RPM.
blade is mass far from the
Exactly
hub,
as expected.
raising
The
moment of
faster the
inertia
rotation,
and
the
demanding
stronger
more
the
wind
field.
energy to accelerate. Fewer blades meant quicker response to gusts, forming a new systems logic. Less area, less drag, higher speed, more electricity.
The
That
airflow
logic reversed a
simulation looks
millennium
much
of windmill
cleaner now.
history.
Yes,
But
reducing
reaching
the
3
thickness
required
by
a chaotic
5%
testing
really
era, where
optimized
bold
the
designs
lift-to-drag
met
ratio.
physics. In the 1970s, ADS, teams in Germany, and the U.S.R. please of the base, argued that a single blade was ideal, less material, less drag, and much higher RPM. On paper, they were right, but reality was harsh. A one-blade turbine needed a huge counterweight, so the total mass barely fell at all. High RPM increased centrifugal loads and accelerated material fatigue, forcing frequent blade replacements and raising downtime and cost. Asymmetry also drove severe vibration. The shaft shook, bearings wore fast, and the tower structure oscillated beyond safe limits. Two-blade turbines fared little better with 180 degrees spacing. Each rotation sends a blade through the tower's wake, causing force swings.
The
That
stabilization
uneven lift
matrix is
produced
holding
gyroscopic
steady.
vibration and
Look
early
at the energy
mechanical
curve.
failure.
It's perfectly within
Sometimes,
tolerance.
after only a
Excellent.
few
We are
years of
clear for the next
operation in the
phase.
field, in the end, asymmetric designs eliminated themselves. What remained was familiar yet surprising: the three-bladed rotor as winner. Not for aesthetics, but for a core rule of rotating systems: a triangle is the most stable shape. balancing forces in every direction. Once 3 blades proved 25-plus-year lifetimes, the industry converged global supply chains, from fiberglass to gearboxes, served one standard. It resembled the shipping container's rise once a standard wins. Every manufacturer adapts, and infrastructure reshapes around it. Standardization lowered costs via economies of scale, simplified training, optimized maintenance, and reduced risk for energy investors.
The stress
Technically,
fracture initiated
3
here,
blades hit the sweet
exactly
spot,
as the
few
simulation
enough to cut,
predicted.
drag, and
Yes,
raise
the
RPM,
thermal data confirms
yet enough to keep
localized
dynamic
overheating at
balance
this
and smooth
joint.
load. They are light enough to reduce inertia, but strong enough to survive storms. Proof that progress often means sustainable simplicity. The 3-blade turbine wasn't a sudden invention, but the result of one. 000 years of selection, keeping what balanced power, cost, and risk. That is the power of minimalism less, but smarter. An evolution where design advances by removing what physics and economics cannot justify.